Welcome to our demonstration of how we upcycle formal specifications for similar implementations with our system Arís. While formal verification of source code has become more popular in many real-world applications, successfully verifying the code requires three critical, difficult activities. These are writing mathematical or formal specifications describing the task to be achieved, writing the source code to solve the task, and proving the correctness of the source code implementation with respect to its specification. In this work, we address both the creation of formal specifications and proof of the correctness of the source code implementation with respect to this specification. We do this by retrieving a verified implementation from a repository of verified code, reusing its formal specification and proof support to create both for a given target implementation. In software verification, the focus is on modular verification. We see an example here with the specification written as a formal contract which specifies the preconditions, the requires clauses, which must hold for the given implementation to establish the postconditions, expressed as ensures clauses. Proving the correctness of the implementation with respect to its specification is handled by a theorem prover. Behavioral properties are typically written as ensures clauses. Safety properties and axioms to support the proof are provided by the user, expressed as annotations in the source code, shown here as invariants in our example. This example will be used in our demo and its verification can be seen at the given URL. In Arís, we illustrate our proof of concept within code contracts, which supports the verification of C# code. As we work on code graphs which represent the implementations, the work is directly transferable to verification tools for other languages, such as C, Java, Python, etc. We now show the code graphs underlying its operation, how graph matching supports retrieval, and pattern completion enables transfer of specifications to new implementations. We note that subsequent use of this verified code drives further reasoning within the Arís system.
We source some specifications at the website Rise for Fun. We can see here there are 3 invariants. Down here we have a method with 1 requires, 1 specification, and 2 statements. So this source code is processed, it's parsed. We examine the parse tree. And examining the parse tree allows us to identify various artifacts such as a root node, the method name, identifiers like variables, their relationship to the method, such as it being a parameter, and so on. As part of the code graph, we also include our formal specification. Now, looking more closely at its graph structure, we can see it contains a block node, which holds a method name. The method contains a parameter. It also contains another block, which includes some assignment statements and so on. We can also see that the formal specification is included on our graph.
So after doing the graph mapping, the next thing we did is to create a tool that would transfer or adapt the old specification from old code or old method to new method. For this, the tool has to identify the relevant columns, relevant rows from the graph mapping. So over here you can see the tool identifies the 3 relevant columns and 2 relevant rows from the graph mapping. So over here the the graph mapping matches this method resize demo with the method read next, and with the variable size0 with the count variable. The tool fetches the target method, source method, and the source graph to identify the code contract. From the source graph, we are able to fetch the code contracts associated with the variable from the graph mapping. So over here you can see the graph mapping showed the size0 variable, and the label associated with it is 2, and the label associated code contract with it is over here is like this one. So from this we are able to fetch the code contract. So the next step is to fetch the code contracts from the source method from the identified source graph. So this is the code contract fetched based on the identification done in the previous step. So once the code contract is identified, the next step is to adapt the code contract based on the target method. So over here the code contract is adapted in a way to the code contract if it is compatible to the target method. So for that, two procedures are done. One is variable name change, and to check whether both are of same type. So variable name change, the variable name is changed according to the target method, and for type match it checks whether both are of same type, both the variables are of same type. So the next step is to place the adapted code contract to the target method. For that, we identify under which method the code contract has to be placed in the target method. Over here, we identify the relative methods from this graph mapping and place it appropriately in the right place based on the precondition or post condition or assert statement. So the end result will give a adapted method with specification. So the next step is to verify the adapted method with code contract. So for this, we have created a verifier that would give the verification based on different parameters. So those are the validation associated with the new method, the number of assertions that has been corrected, and contract density and number of methods that has been analyzed. So this verifier will give a result on how much effective the transfer has been. As over here you can see the example over there, the 100% validation. Like this, we can examine how a adaptation has been properly executed.
Successfully verified methods, along with their new specifications, are added to the casebase, and these can potentially reach new, initially inaccessible implementations, thereby extending the reach of those specifications. Okay, thank you for watching our presentation on Arís to the ICCBR 2021 conference.